All right, so today's lab is on momentum and energy conservation, in specifically in an elastic collision. Let me go over the instructions. Let me pull those up. Okay, once we get to lab 10, before we'll get to the instructions. Fairly straightforward. I think so. We're going to be sort of watching a video on two cars that are moving on a track. This is going to be like an air track. So think of like a think of a air hockey table. You know, there's like little air jets that make the disc glide. Let me pull up the video. So this video I'm talking about is right here. So let me get the video. So there are two, they're called gliders. You could call them gliders or cars. They're going to be moving along this track, and they have these little rubber band attachments that make them perfectly bounce off of each other. You're going to be able to see how quickly they come in and how quickly they will leave the screen. So let me play this. And I know it may be a bit choppy over Zoom. So I have, you could also do this for your measurements. You could go to the playback speed and put it on quarter speed, or you could have it at normal for all of your measurements. Just whichever you have it on, make sure you take a note of what to change. So on quarter speed, let me put this like that. On a quarter speed, hopefully that's less choppy than I know it can be. You see they come in, and at a certain point, they'll bounce off of each other. This is called a perfect elastic collision. Elastic, so I think of like a bouncy ball, a elastic ball. Let me this up. Right, yeah, you could say this is a frictionless surface. Let me pause it. You see the little dots on this track. Those are like the air jets are coming out of there. So it's very close to being frictionless for this test. You would be doing this in person. Unfortunately, we can't. So quarter speed, that's where it ends. Something I just figured out, is that you can, for your measurements today, if you right click on the video, you can loop the video. So you don't have to keep repositioning where it is. So you can just let it go. So I'm going to let it go while I talk for a bit. What you're going to do is take some measurements. Let me put that right there. So, and the video is looping. You're going to take some measurements on where they are. You see on the screen, there's some sticky notes to sort of point out some measurements on the track. There's this little measuring tape. Those are in centimeters. Something that we're going to need to do is find the speeds before the collision. So this is before the collision, and this will be considered after the collision. So going to need to find the speeds before and after for the card on the left and the card on the right. A way to do this is use the measurements that are given on the track. So they're in centimeters. We know they're centimeters. And we could figure out a time. So how much distance does it go in a specific amount of time? So we have distance over time, that's velocity. We get the velocities before and after. And with those, we can have the momentum of each cart before and after the collision. Let's just see it one more time. Where it specifically happens, where the collision specifically happens, isn't quite important. So say I start, let me pause it. I can take, a measurement, for example, let's go like this. So how I would measure this is I would see the leading edge of one of the cars. So see the car on the left, you can see it. It's on the screen now. And I would say that's 60 to maybe 62 and a half. And then I'd play it and get it to where I want to measure the next position. Let's say, something like right there. So I have that distance and I will measure it with like my own stopwatch, my phone separately, a time. Something else that was brought up that might be easy as you could put like actual sticky notes on your computer screen to take a time. So if this thing is looping over and over again, let me put it normal speed. So if this thing is looping over and over again, you could always just like time it when it goes beyond the sticky notes and do your measurements that way. So this is normal speed. Just like that. So however you want to do this, this is the video we're basing the experiment on. Here, let's watch it one more time. And this is a very interesting problem in that we're having the two come together and collide. They're both moving. Originally, or in many other problems, we'll be finding the mass. So the masses of each cart are going to be given. So the cart on the left, mass is given, and the cart on the right, the mass is given. And I believe, right, if it is at quarter speed, that means our time we will have to multiply. I think you'd have to multiply by 4 instead of divide by 4. So like 1 second is, or 4 of your stopwatch seconds is 1 second in the video. If that makes sense. So you're on the right track. Yeah, so masses are given in the instructions. Let's go right here. So masses, the left and the right are given right here. Okay, so what is specifically the problem? Why are we doing this? So there are 2 ways to find, before and after momentum. So, or 2 ways to analyze the problem. And we're going to arrange them as like case A right here and case B right here. So how are we going to compare the momentum before versus the momentum after the collision? In case A, we can look at the total momentum of the 2 mass system before the collision and the total momentum after. Okay, so that's case A. We could try doing that, see what we get. And case B is just the gain or loss of momentum in one cart or one mass is the same or as the gain or loss of momentum in the other mass. Let me, before I, just say this and leave, I want to do, a normal case, and then I want to do a, case or at least introduce the case of what we're going to do in my notes. So let me do that right now. So that's and like that. Okay. So let's do a normal case where one car is moving and one car is stationary. It's staying still. So let me title these notes. Elastic has 2 L's. No, it has 1 L. Ugh, can't spell today. So for an elastic collision, it's something that bounces off of something else. Let's take mass 1, something that's right here. It's a glider or a cart. We'll call mass 1, and it has a velocity 1 of 0 meters per second. And we have to always remember velocity is a vector. So I'm going to have that vector sign above it. Okay. And I'm going to move this. I want this right here. And we're going to be sort of pushing a second mass or a second, car towards it. It's going to be over here on the right. That's going to be called M2 for mass 2. And it has its own velocity. Let me also, I should specify, I'm going to go like this, velocity 1, I for initial. This is going to be the velocity 2, I for initial. 0. And let's say this one has a velocity of 3 meters per second. Again, this is a vector. And since it is a vector, the direction is important. It's going to be going to the left. So it's going to be negative. So always, in any problem, we're going to have to be consistent with our notation. We're always going to say to the right, it's positive. We're always going to say up is positive. Okay, so for this case, this one's staying still. This one's moving to the left. And I'm going to put this, let me label. This is the initial case. Okay, so what are the momentums of each of these cars? So first off, let me put it up in the corner some important equations. So I'll say momentum is P equals just mass times velocity. We also have to remember, though, you look right down here, velocity is a vector. Velocity is a vector, so that means momentum is also a vector. The direction is important. Okay, so we have a way to find momentum since we do have a mass. I don't know. let me say like the mass 1, that's like 7 kilograms, and we'll say mass 2 is, what did I say, 5 kilograms. So now that we have, known values, we could find momentums. The way we commonly would do that is in our instructions, like case A. So we would find the total momentum before. So I'll say momentum total initial is equal to momentum total final. So you just compare before and after the collisions. And this is case A in our instructions. And that works very well when something is not moving like this. Okay, so in this case, let's do this problem. So the total initial momentum, that is just, let me do this, momentum of the first object plus the momentum of the second object. I'm going to say I, like that, is equal to the momentum of the first object final plus momentum of second object final. Okay, and the last sort of intermediate step before I could actually do stuff is, or put in some values. I can go like this. So mass 1 times velocity 1 initial, mass 2, velocity 2 initial. But now I see over here, I need to actually give a case for a final. That's what I forgot to do. So I just needed to do that and I forgot. So let me put the final case. So this is the initial. This is before the collision. So let me make a final where they hit each other, sort of bump into each other, and have a perfect elastic collision. And, I'm not going to make it easy, so I'm going to say that both of them are moving. So that first one, since he's moving to the left, I'm going to say -1 meters per second. And actually, let's find that second one. This is a good sort of warm up for our lab. Also, just for collisions in general. I'm gonna say question mark. This is the final. Actually, let me make this 2. Okay, so now let me finish down here. Mass 1 times velocity 1 final, mass 2 times velocity 2 final. If you're able to follow along with this, this is the extent of many problems on like a homework or something. Plugging in all of this, I'm going to leave the, I'll keep the units in. 0, it's not moving to begin with. 5. And since it's not losing any pieces as it moves along, the masses stay the same, both before and after the collision. And this is after the collision is on the right side, right-hand side. And this is the unknown. Okay, so looking over here, that's 0 plus a minus 15 kilograms meters per second. This is minus 14 kilograms times meters per second. 5 kilograms. That's okay. So adding this over, we get minus 1. So wasn't as direct as you might have thought in the beginning. So let me this. So minus 1/5 meters per second. Okay, so this is sort of a warm-up problem. This isn't quite what we're doing. I just wanted to at least show the process of why it's good to use case A in many scenarios. We look at the total momentum before and the total momentum after the collision. Okay, so let's look, or I'm at least going to introduce something else that we're doing in the lab. Okay. Okay, so now that we've done a little warm up in today's lab, we're not looking at one block that's staying still, the other one's sort of coming in and hitting it. We're looking at the scenario where one block is moving in one direction and another block is moving in the opposite direction. And we're going to see which way we can do this momentum analysis we've done before. So up here, up at the top, we've done total before, total after. So that's case A. Is look at the total momentum total before and compare that to I'll just say like versus total after. we will see we will see that something sort of fishy happens when we do this, when there are two things that are moving in this specific way. Once again, remember that we need to include the direction. So momentum is a vector. So this one has a momentum. It's a vector that is positive because it's moving to the right. This one, V2, is a vector. It's negative. It's moving to the left. And there's this funny thing that happens when we are doing sort of that, calculation like this. Before versus, whatever, after. There's this funny thing that happens because of these, vector components. That's what we're going to look at and why we might not want to use case A for, this arrangement, this scenario. The other thing that we could try doing is using what is brought up in case B in the instructions. It is saying to do something like this instead. It's saying instead of total, of one car plus the second car, total before and total after, what if you just look at the change in momentum of one car, throughout the collision versus the change of momentum, that's a vector, of the second car. So however one car, changes, this is, remember this delta sign, so that would be like P1 final minus P1 initial, like that. So this is the second case. This is the other way to analyze this collision before and after. Final minus initial. Okay, so we have these, two ways of thinking. Which one is better? How do we tell which one's better? We see which one is perfectly conserving the momentum. So what that means is I have this versus sign. If something is, I'll leave it. Let me go like this. Things at the top are going to be tiny. So if we have something that's conserved, it is perfectly equal. So like momentum conservation and energy conservation means that the momentum's not going anywhere. All of the momentum can be found in either car. So conservation means that's, before equals after perfectly. So we're going to try to figure out which one represents energy conservation better, case A or case B. We're going to be doing the same thing for the kinetic energy of these cars. So let me go like this. If you guys are following along and you need to re-see something, just let me know. So it's going to be the exact same thing except with kinetic energy. So case A, kinetic energy, we're going to look at the total of the two cars before and the total after. And case B, the other thing we're comparing this to, case B, is just the difference in, just looking at a single car, how it changes versus the other car. The change in kinetic energy of one car. And I believe, with these case B values, we may expect, something that might be positive or negative. Let me do like that. Just want to specify that that is okay. And I'll also put that up here. Actually, no, let me just put negative. So that's saying like whichever, like if one car loses, so up here, if the first car loses some momentum, it is then given to that other car. That's why I'm putting this negative sign in there. Hopefully that makes sense. So if not, I could maybe show it with a picture. Again, whichever kinetic energy is lost from one car is then given to the other car that it's colliding with. That's why I'm putting this negative sign. Okay, so there are two cases for both kinetic energy and momentum. I'm going to clean these notes up a bit, make them look a little neater for you guys, and I'll put them on canvas. Let me also put up here kinetic energy equation. Kinetic energy is 1/2 mass times velocity squared. All right, so are there any questions with, this is the warm-up. Are there any questions with what we're going to be doing? Basically, finding the velocities is what we're going to be measuring. And with those, you'll be able to find momentums. And you're just going to, take your values and do one type of analysis. That's case A. And then you're going to do a different type, slightly different, which is case B. You're going to see which one shows momentum conservation. You're going to do the same exact thing with the kinetic energy. So once you have the values measured, you just take them in and do one type of analysis, case A, and you're going to do the other type, case B, slightly different. I didn't specify, but I think you get it. So it's kinetic energy of the first car final minus kinetic energy of the first car initial, and so on. Pretty, you know, I would say this lab is not as bad as some others. It's pretty straightforward. If you guys have questions, let me know. I don't think I have anything that I need to check off for you guys. So if you want to stick around and ask questions, go ahead. Let me, yeah, go like that.